Okay, we are asked to do a definite integral. So I notice I have these numbers here, which tells me it's a definite integral, which means what it really means is a sum of function values on some region, or we can think about that in terms of areas. So you don't have to draw a picture of the graph, but it might be helpful to think about that. So if I think about just graphing the function, f of x equals x over 1 minus x squared, and you can use your graphing calculator to help you with that if you want. You might notice this function isn't continuous everywhere. It has some vertical asymptotes at 1 and -1 and a horizontal asymptote at 0. I'm not interested in the entire graph. I'm really interested in the part of the graph between x equals 2 and 4. And one important thing here is that for this function, between x equals 2 and 4, the function is actually below the x-axis. So we're really talking about this part. And since the function has negative y coordinates on that interval from x equals 2 to 4, I should expect the answer for this definite integral to be negative. Again, thinking about that in terms of a sum of function values times widths. So when we first talked about what definite integrals mean, the function values, the y coordinates on this region are negative. So I should expect this answer to be negative. The other important thing to notice is that when we talked about fundamental theorem of calculus, that only works if your function is continuous on your interval. This function is not continuous everywhere. It has discontinuities at x equals 1 and -1. But thankfully, it is continuous on the interval we're being asked to evaluate. So two important things that even though it didn't ask you about the graph can help you think about. First of all, this function isn't continuous everywhere, but it is continuous on the interval we want. So I can use fundamental theorem of calculus to evaluate this. Also, the answer should be negative. It's representing this area of this region that's below the x-axis, where I have negative function output values. Okay, so to actually evaluate it, we're going to use fundamental theorem of calculus, and so I need to find an antiderivative. So we have antiderivative rules for x to a power. We have antiderivative rules for 1 over x. We have antiderivative rules for constant functions. So thinking about all those different rules, none of them are exactly this. I really can't do any algebra to simplify this. So if it's not a basic antiderivative, and I can't do some algebra to simplify it so that it is, it's probably going to be a U-substitution. So thinking through what to let U equal. So I have a lot of different choices here for what I could let U equal. U could just be x. U could be, I'm just thinking about the different pieces here, x squared. U could be 1 minus x squared. U could be x over 1 minus x squared. Probably some other things that you might think through, but these are kind of all the different pieces that I see here in this function. I don't obviously have a function inside another function here, so this one's maybe not as easy to think through what U should be as some of the other ones we've done. So in general, if you choose U equals x, that's not wrong, but all that's going to do is change all of the letters from x to U. You'll just replace all of the letters from x to U. So you're still going to end up having to try to find the antiderivative of the same function, just with u's instead of x's. So while there might be times you want to do that to change variables, that's not really going to simplify the integral and usually not going to help you. If you could find the antiderivative in terms of x's, then you would just do that to start the beginning. All right, thinking through these other choices for what to let U equal, how you decide what is the best choice for the U substitution is in thinking through what the du would be, what the derivative would be. So you might notice that for these two, you end up with similar du's. So if I had U equals x squared, then my du would be 2x dx. If I have U equals 1 minus x squared, then my du would be, derivative of 1 is 0, and then negative 2x dx. So I end up with almost the same du for both of these. This one if you think through the du for this one, you're going to have to use quotient rule to find that derivative, and you end up with a big mess. So how you choose what is the appropriate u to do is that your u and your du have to account for all the variable parts of the function. So if I think through like using quotient rule to find this derivative, I get a big old mess, which I don't have that derivative here. So this is not going to work. So that means my choices are these two. And they have almost the same du, constant times x dx. I have x dx here. I can handle the extra constant. So how you decide between these two, which one is the appropriate one to use, is in general, you want to use the one that accounts for more of the function than less of the function. So this u accounting for that entire denominator is a better choice than just letting u equals x squared. I could do the problem letting u equals x squared, but then I would have to do another u substitution or maybe double u substitution to finish it. So if you can let u account for more of the function that you're integrating, that's usually a better choice. All right, so this is the one I'm going to use. So I'll rewrite some things over here. So I like to match everything up over here. So if I'm going to let u equal 1 minus x squared, that is going to account for this. My du is negative 2x dx. The x dx is going to account for that. I do have to deal with the negative 2, so I can divide that over to the other side. So in place of the x dx, I'm going to substitute in negative 1/2 du. And then when you're using a definite integral, remember that these are x values to start with. And so if I'm converting to u, I need to convert those as well. So when x is 2, u will be 1 minus 2 squared. So 1 minus 4 is negative 3. And when x is equal to 4, u will be 1 minus 4 squared. So 1 minus 16, so negative 15. So those are going to be my new limits of integration. So in place of the 4 and the 2, we put these values. All right, so my new integral is going to be the integral. Well, that one is tired. All right, the integral from, let's see, the lower limit of integration 2 corresponds to negative 3. So I have to put the right number in the right place. The upper limit of integration 4 corresponds to negative 15. In place of the x dx, I'm going to have negative 1/2 du. I can pull the negative 1/2 out front. And then in place of the 1 minus x squared, I'm going to have u. Okay, so now I'm ready to just find the antiderivative. Don't lose this minus sign that's up front here. So I'll have negative 1/2. The integral of 1 over u du is natural log of absolute value of u. Those absolute values will be important on this problem. And then we're going to be evaluated from negative 3 to negative 15. So then we found the antiderivative, and then using fundamental theorem of calculus, we're going to evaluate that antiderivative at each of the endpoints. The upper one is the one you put in first. So negative 1/2 ln of absolute value of negative 15. And then minus negative 1/2, so plus 1/2 ln of absolute value of negative 3. So technically, I could leave my answer like this. You can do a little bit of simplification if you want, and I would recommend getting a decimal approximation also, just to make sure your answer makes sense with what we talked about at the beginning. So how could you simplify that? A couple of things that you could do here. Absolute value of a negative number will make that number positive. So this becomes negative 1/2 ln of positive 15, and then plus ln of, same thing here, well, absolute value of negative 3 is 3. I could leave my answer like that. There are some properties of logarithms that you could use as well. You could factor a 1/2 out. Maybe I'll factor that 1/2 out. You don't have to do any of this unless it's helpful to you in making sense of your answer or in simplifying your answer. If I factor the 1/2 out, I'm going to go ahead and do that, and then I'm going to write the positive term first. So ln of 3 minus ln of 15. There is another property of logarithms that you might remember that says if you have natural log of a minus natural log of b, you can rewrite that as natural log of a over b, 3 over 15, which reduces to 1/5. If you like. There's another property of logarithms that says if you have a constant out front of a logarithm, that constant out front can become the power of the argument of the logarithm. So I could have ln of 1/5 to the 1/2 power, or ln of square root of 1/5. Okay, so all that stuff is just, if you're having fun with logarithms and you want to do that, it's perfectly fine to leave your answer in this form. And whatever form you have that answer in, I would probably get a decimal approximation just to make sure that your answer makes sense. Again, we talked about that this answer should be negative because this function has negative function output values on that interval. You could also get some points from the original function and just think about like how big should that answer be. So when x is equal to 2 in the original function, I have 2 over 1 minus 2 squared, so negative 2/3. And then 4, and then 4 over 1 minus 4 squared, so negative 4/15. All right, so these values are pretty close to 0. These y coordinates are pretty close to 0. So this is going to be a negative answer, but fairly small in size. If you just think about like using rectangles to sort of think about how big that should be. All right, so I'm going to type this into my calculator, which I already did, and got a decimal approximation of about negative 0.8, which makes sense based on thinking about the function. I know it should be negative. These are fairly close to 0, though, so if I just think about how big the area of this region is, it should be fairly close to 0. So negative 0.8 is a reasonable answer. All right, we'll look at one more of these in the next video.